All right, so you may have had an X-ray in your life, hopefully not, because usually it's to check if something is wrong, because it's used for medical imaging. Have you ever wondered how they were generated? So this is what we're going to be looking at in this video, how those X-rays are generated to then be used for medical imaging or other applications. So we have an X-ray tube over here, and so some interesting elements you have here would be the metal target, and then you have a potential difference here, which is going to accelerate electrons over here. So fast enough, and then so essentially they're going to gain energy, and then they're going to hit the target, and X-rays are going to be generated. So let's take a look at how exactly those X-rays are generated. They actually are generated due to two different phenomena. So one is Bremsstrahlung, which is actually from the German meaning breaking radiation. The idea is that as the electrons hit the target, they're going to start decelerating, and as they decelerate, they're going to radiate, but this is going to be something continuum. This is which is due to this deceleration, and you get this curve here, which is our Bremsstrahlung continuum of X-rays that are being generated. Now we can see that there's something very different also happening here, because we have these two large peaks, K alpha, K beta. So what is happening here? So sometimes you're going to have electrons that are actually that have enough energy that they're going to knock out an electron in the K shell of the atom of the metal target. So we have that metal target. An electron is going to knock out one of the electrons in the K shell. What's going to happen is that now that that spot is available, it's actually a more stable state. So an electron that is in an upper level is going to travel down to the K shell. As it's doing that, it's going to emit radiation. And those are the peaks that you see over here. So the two different peaks are for K alpha is if you get an electron from the n equal 2 level dropping to the K shell. And K beta is for an electron that will be coming from the n equal 3 level to the K shell instead. So we can actually figure out the energy and then the energy levels, and as a result, we can figure out the wavelengths to show that they're X-ray radiation. But it's a little bit more complex than what we would have seen for the hydrogen atom. So remember here our target atoms are metals. So definitely we have a lot more electrons than we do have in the hydrogen atom. So in ways we can still use what we've learned, but we have to make some modifications. So if we look at the energy of the K shell electrons, we had derived what it looked like in the hydrogen atom. However, now that we're considering something that is going to have two electrons in the K shell, so okay, so for if you're at n equals some number, you're going to have this. And that's essentially something that looks very much like what we saw that was derived from the Bohr's model of the hydrogen atom. Now, if we look at what's going on in the K shell, that's a lot closer to the nucleus, we have to make some modifications, because so if you're trying to look at the energy for one of those two electrons that are in the K shell, remember we have two possible states, so we have two electrons there. But we have to worry about something that's called the effective charge, because each of these electrons is not just going to experience the positive charge due to the nucleus, because essentially we also have that positive charge partially canceled by the other electrons that is there. So instead of feeling all the effect due to the charge, the positive charge in the nucleus, we have something that's going to actually be less than that because of the electron that is there. So we have to modify a bit for the energy in the K shell so that we can calculate the delta E, the change in energy as we go from n equal 2 to n equals 1 or n equal 3 to n equals 1, depending on if we're looking at the K alpha or K beta radiation. And so the energy in the K shell is now modified and given by this. So Z minus 1 again is coming from this, the fact that we have this effective charge that is seen by each of the electrons. And you can see that if you look at the energy in one of the outer shells, so n equal 2, n equal 3, versus the K shell, you can then calculate a change in energy. And then from that, you can find the wavelength of your radiation. So you can try to do an estimate for copper where Z would be equal to 29, for example. So the next application we're going to look at is the laser. So stay tuned. Thank you. Bye.